a teacher for thermodynamics and molecular physics this semester. So I'd like first to congratulate you with the start of the new semester and wish you the pleasant flight into the knowledge. And at first, I would like to start with some organizational stuff. And first of all, you would be given an example of program syllabus for this semester. The syllabus contains the topics which we are going to study. So that's followed by recommended literature and further reading. So if you want to know something beyond the lectures, and I encourage you to do so, you need to read the textbook, because the time for the lecture is limited. So it would be stuff, but that would be for your well, self-studies. So these are recommended books. Also, we would have an assignments. In this semester, we have 2 assignments. One assignment is for thermodynamics. The second is 3 types of problems. Problems of 0 type. The problems of 0 type are designed for you for preparation to the lecture. So I encourage you to solve, or to at least try to solve these problems before you go for the lecture and seminar. Because if you do so, you would be better, you would be better prepared for what is going to come during the lecture. So that's the 0 level problems. Problems of the type 1 are the problems which I'm going to solve during the seminar. And problems of the type 2 are for you to solve after the seminar for the assignment. So I would check how you solve the problems of the type 2. If you for some reason miss the lecture or miss the seminar, and then please add into your assignment, into your assignment also the problems of type 1, which I have solved during the seminar. So just that you also remember how they are solved. And finally, there are text problems. Those are the problems which are absent in our book with problems. And the book is, as usual, Irodov Problems in General Physics book. As far as I understand, you have used this book during the previous semester in mechanics. And the second chapter of this book is devoted to thermodynamics. So mostly the problems would be from the second chapter, but there are some exceptions, of course. And these text problems are the problems which I didn't found any kind of an analog in the problem book. So I have designed special space for them. So I have them. So after this lecture, I'm going to share everything with you. So as of now, I have your names and emails, and I would be able to do so. And also, just to keep some kind of track of your presence during the lectures, I would like you to write down your name here, and please underline the part of your name which you would like for me to call you. So like the most of, and sometimes it becomes well, I don't know which type of your name I should call you. So that's why I encourage you to underline the part of your name which would you like to call by. So okay, for this semester we study 2 subjects. The relationship systems which consist out of many different particles which move chaotically and affect each other. Perfect example of molecules, they collide, happens in between them. Properties of those systems. So of course we are not in, this is not mechanical. I try to speak somewhat slower now in order to get over those glitches with sound. So the interest in the particular details of those motions. So I'm not interested in the position and the velocity of each particular molecule. Have as an aggregate, so as a system. Physics, different approaches to studying these systems. So that means that we observe the system and we see some, and we try to figure out the laws which this looking at it. So I'm particularly interested in the structure of inner workings. The scientists of that age were put molecular without absolute evidence of the molecular structure of what was around us. This was, I think, this was the only rigorous approach to study of such systems, because molecular physics, we know the structure, we know the molecules in there, they move some way, and from that we can get to some conclusions. But if you are confident about having molecules there, you can only restrict yourself to this phenomenological approach. Of course, the results of this study using these two different are not contradicting, so they agree with each other. So sometimes it is convenient vice versa. So probably also an assistant says that everything is okay on our side. Probably there is something happening with the internet connection. So, well, okay. So now I'm going to continue with, for today's lecture we have, and to start with the so-called minus first. Thermodynamics is constructed in a way which is somewhat similar to Euclidean geometry. It has some kind of statements which are accepted as truths. Statements we derive the more complicated properties of the systems. Well, minus proof some kind of a very obvious stuff. It says that if we after some time, sometimes it is fast, Sometimes you need to wait a bit longer than that, but after some time, the system equilibrium. And this equilibrium has a very peculiar property that the state be described small number when this statement is omitted and it is considered like something which is given. For example, when in school, when you have started studying the gases, then, well, you know that the state of the gas can be described by its volume, its pressure, its temperature, and, well, but the existence of these variables, which a small set of variables like pressure and volume, which can describe a state of the gas, is postulated. Sometimes it's postulated tacitly, so without saying, this is which is implied. So you start studying, but it's already implied that you can use a small number of variables to describe the state of the system. It's not always a given, which is not in the state of the equilibrium, then the state cannot be described by a small set of variables. For example, when you have the sound waves propagating in the room, that means that at different space coordinates of this room, at different points, the pressure is different, because sound waves are actually fluctuations of pressure at different points of space. So that's why instead of one pressure variable, you should describe the whole pressure distribution inside the room. But when you have thermodynamic equilibrium, then a small number of measurable variables can describe a state of the liquid. Okay. First law of thermodynamics, and, well, it's kind of a miracle, because there is a huge number of those particles, each of them moving in their own way, and each of them interacting chaotically with other particles. But for some reason, they relax to this thermodynamic equilibrium. So if you prepare a system in a state which is far away from thermodynamic equilibrium, then after some time, it comes to this state, and then that state doesn't change anymore. Of course, we need, yes? Okay, so there's a problem. Okay, I'll try to be patient. So the pressure and volume, and of course we need some variable which describes the amount of, so the amount of matter. The amount of matter characterized in moles, and also be characterized in, well, you can specify as the mass of your gas. So that's enough, only 3 variables, instead of all of the coordinates and velocities of all particles out of which that gas consists. So if we have n particles here, describe a microscopic state, so to obtain full information about the state of this gas, I would need molecules have some complicated shape. I also need some angular positions, some these rotational velocities and rotational coordinates. So at least 6 n coordinates are required to fully describe the state of the system. But when the system in the state of thermodynamic equilibrium, well, I need only 2 of them. Well, actually 3. So that's a huge decrease in the number of variables. Okay, now we are going to... The concept of temperature is something which is invented in thermodynamics. It is something which more. So to окей. Ну или вот так как-нибудь. Ага. Okay, Zero's law of thermodynamics. It is formulated quite weirdly. If you see this for the first time, it says that if systems A and B are in equilibrium with each other, and the systems B and C, the same stuff, are in equilibrium with each other, then A and C are also in equilibrium with each other. At first glance, there is no relationship to any temperature at all, but believe me, this is the statement which actually introduces the temperature. Now I'm going to expand, explain what's actually meant here. In equilibrium with each other, what it means. If I have a system, I can bring them into contact with each other. And after I bring them into contact with each other, then their states described by those do not change. So as I bring them in contact, so as I allow these two systems to interact, then the state of the system doesn't change. So that means that these systems are in equilibrium with each other. And same stuff for if I do so system in B and C, then also nothing changes. And so that means that if I bring into contact the systems A and C, then they would also be in equilibrium with each other. Of course, there was some intricate matters about here, because when I bring them into contact, what it means in equilibrium, I can their volume. So for example, their pressure can be different. So if I take them together and their pressure is different, and I allow them to interact mechanically, then of course the system would expand, the other system would contract, and there would be changes. But I allow the systems to interact in such a way that this absence of mechanical equilibrium doesn't matter. So I bring them into contact. I can assume that I have, for example, like a rigid wall which separates these two systems, which allows them to interact, but doesn't allow them to compress or to expand each other. So I would like to add here molecule. So for this particular type of an interaction, thermal equilibrium. Okay, so then to introduce the temperature. Let's go here. So now we're going to another system, system T. Yes, system, or let's say TH. Moment. Bring in contact with any other system. And of course, as a thermodynamic system can be described in its equilibrium number of variables, but I would like to pick the number of variables to only one. So let's say if this system, for example, is gas, then I'm, for example, the pressure constant. Change. Volume can be used to characterize any other system. I can bring the system and measure the volume after the thermal equilibrium is established in the compound system out of A and TH. Characterized the state of the system B by one variable, the volume of the system TH. And if these two volumes, if these two variables are equal to each other, then according to Zero's law of thermodynamics, systems A and B would be in thermal equilibrium with each other. But if these two variables are different, then if I bring these two systems in close contact to each other, then these characteristic volumes would change, because in absence of thermal equilibrium, this equilibrium would be established after some time. So after I bring these systems with different, let's say those are temperatures actually, in contact with each other, sometime those temperatures after this thermal equilibrium is established. So essentially, while formulated this Zero's law of thermodynamics is the main law which allows you to arrive and to establish the concept of temperature. So to some measurable stuff like volume, I now have additional variable which can describe the state of thermodynamics. And of course, I can introduce any function of those volumes volume of the thermometer. And as I introduce this function, I establish a temperature scale. One of the most famous temperature scales is Celsius temperature scale, when you assume that the melting point of water happens at melting point of ice, while the of vaporization. So, and is how the temperature scale is established. Actually, the values are just a convention. So you declare something first, and then you explain the procedure which allows you to measure temperature. And this procedure should measure temperature in the same way in different parts of the world. And that would allow different people from different countries and whatsoever to compare their results. In thermodynamics, each law is related to a new variable which is assigned to the state of the system. So after the minus first law, I now have few variables to describe the state. After the zeroth law, I have also a temperature used. Now, law of dynamics. The first law introduces not just so let's try to understand what does this concept of internal energy mean. So as I said, thermodynamics is based on observations. There are some types of energy there. So some kind of a liquid, and a droplet of liquid moves in space with some velocity as a whole structure. Then, of course, you can find the kinetic energy of this droplet as mv squared over 2. But it was discovered that some processes in nature do not conserve this observable mechanical energy. So let's say, for example, you drop some brick onto the ground, number of collisions, but after some time, the brick remains on the ground. That means that the kinetic energy of the brick, but it has potential energy in the gravity of mgh, where is the altitude of this brick. But in the final state, you see that kinetic energy is also 0, while the potential energy is 0 too. So there is no over concept of internal energy. So the brick contains not only kinetic and potential energy, but it also ground below the brick also has it. And after this process, actually what happens, the part of mechanical energy which has been lost in the process has turned into the internal energy. So you don't even need a concept of molecules, atoms to understand that something happens, and you need to introduce some new quantity in order to explain. Otherwise, the energy is conserved. Of course, we know now out of atoms, and so you can ascribe the energy or mechanical energy of the internal motion to this internal energy. So of all molecules times squared velocity of all molecules, which are of course random variables, and sum of a huge number of random variables, plus also there is also a potential energy of interaction between different molecules. So you need also to include the energy of pairwise interaction between molecules, some kind of a W of REI or RG. So the potential. And if you sum up all, then you quantity which is internal energy. Quantity fluctuates. Prepare what actually is meant by internal energy is the average value of U, the average. Of course, is that this average when the system is equilibrium, and this energy is a function of macroscopic values which describe the state of the system in thermodynamic equilibrium. And this is not very evident. But you can introduce energy which is a function of state variables. Okay, then you can, after you postulate the existence of this internal energy, yes?
The law, the n is sigma n.
Here are okay. Нашла какой-то контакт, наверное.
Если что, я вам покажу.
Мы разделаем на минуты 3.
Давайте попробуем.
Окей. Now that we have postulated the existence of this internal energy, we can formulate from your high school, and it says that that of heat is the system plus Lewis. But as I said, the most important part of the first law of thermodynamics is the existence of this function. So this is actually a non-trivial part, because in here you have some of random variables, and in here you have something which is not random anymore. And well, additionally, there are different types of energy transfer. Energy as heat. Transfer of which happens. So you can just bring to even though nothing happens, some amount one system to so, hopefully, but well, as any empiric laws which we like consider in laboratory stuff or which apply to this stuff which see on Earth, we hope that they extend to the universe, but there is no guarantee, of course. So
because the universe in this moment is polar and polar and polar. So it's a moment that will arrive to equilibrium state.
Well, that's the disputable topic because the stuff is described by cosmology, and the cosmology is an interesting type of science which combines in itself the theory of gravitation, thermodynamics, and mechanics, and so on and so forth. And the problem is that in here, these laws assume that we live in a let's say, uniform space-time, or let's say that if I, for example, move in hundreds, out of the experiment would be the same. Cosmology assumes that the space itself, it's not like the universe, the space itself is under the process of expansion or contraction, which is described by the laws of gravitation. And that means that some of the basic stuff in here is violated. And secondly, the problem about the universe is the following. As I have postulated by minus first law of thermodynamics, each system reaches the thermal equilibrium after some time. But the problem is that this time grows and often grows exponentially as you increase the size of the system. It's, as you see in surroundings, yes, you see living people, you see life, and everything you see is actually a deviation of thermal equilibrium, because thermal equilibrium is planet which doesn't have any kind of a motion here. But what we have here, a state which is far away from thermal equilibrium. And this state is far away from thermodynamic equilibrium for a long time already. The same applies to the universe. The relaxation processes are so slow that the universe itself cannot be considered a thermodynamic system in the equilibrium. It has stars which have different temperatures. It has planets which are much colder. It has some kind of particles moving in space which have the third temperature. And that's why while I can describe some part of the universe by thermodynamics, it is quite difficult to apply it to the whole system. So that's the main problem. Yeah.
If we need to more accurate, we need more complex.
Yeah. So first we start with the simple stuff, like systems with thermodynamic equilibrium. But of course, in nature, there are lots of types of the system which are beyond the state of thermal equilibrium or thermodynamic equilibrium. And to describe those, some expansions of this science are being introduced, like non-equilibrium thermodynamics and some quantum theories which also describe systems beyond the thermodynamic equilibrium. But if you consider like some small system, like for example ideal gas, then the time which is required to reach the thermodynamic equilibrium is really fast. So, and you would see that in your lab practice, because you would change the state of your gas and you would see like how fast it becomes in the state of thermodynamic equilibrium. So that's usually, if you have mechanical system, it reaches equilibrium after amount of time, for example, like the size of the system divided by characteristic time. But a larger system, like here Earth, or if whether point of space here. But if we have Earth in the state of equilibrium, not valid even on the scale, of the city. Not even saying about the scale of the universe. So that's usually how it happens in physics. We cannot immediately describe everything around us, but we try to figure out some simple system to which we can found some theory which explains it. And then after this explanation is here, then we try to expand it further and further to include more and more general cases. Okay, even the energy conservation law is not valid. Like here we state that there is energy conservation law in the first law, but it's not valid when you speak about short amounts of time, because there is this phenomenon in quantum physics when virtual particles appear in vacuum and then disappear again. So if you look at the time scale, which is very short, then you can observe violations of energy conservation law. But on the larger scale of time, the energy conserves. So that's everything is here is quite complex. Okay, we can start or we can continue. Okay, I have said about some fundamental stuff, and I would like to make a transition to a more practical stuff, which can be used in problem solving. And for this, we need a new concepts. One of them is related to the zeroth law. As I said, we can ascribe temperature to any state of the system. So the equation which determines the temperature as a function which fully describe the macroscopic state of the system is called equation, thermic equation. One of them you should already know, the equation of state for the ideal gas. So can anyone say me equation of state for the ideal gas? Oh yeah, so I hear some. So I multiply pressure by volume and amount of gas times this is called universal gas constant. This is temperature. Universal gas constant actually appears as a result of our convention or the choice of the temperature scale. So, so choose the temperature scale differently, then this gas constant, of course, can change. But so since we are limited to this, mostly we have this Kelvin temperature scale in thermodynamics, and that says that the universal gas constant should be 8.31 joule. Okay, here is the matter. I have a question about the amount of matter. How can I determine the amount of matter? So
number of moles for the.
Yeah, that's number of moles. Yeah, so but what is 1 mole? Yeah, that's the huge amount of molecules, which is called Avogadro number, which is equal to the Avogadro number. Then you have 1 matter. Avogadro number is 602 times 10 to the 23. And that's the huge amount of molecules. And for example, 1 mole of oxygen weighs mole of oxygen. Okay, so the molar mass of oxygen, of atom of oxygen, is 16 gram per mole. But if I have oxygen in its gas state, that, yeah, O2, so the O2, so the molar mass of these molecules is 32. So that would weigh 32 grams. Good. Okay, so now we go to slightly more complicated topic. After this, I would change to the mixture of gases. So let's say I have a mixture of oxygen and nitrogen. Yeah, so 1 mole of each. Well, first of all, what would be the equation of state for this mixture? That's slightly more complicated topic. Yes, that when you start a single, well, uniform matter, then it's very simple. But well, now I have a mixture. Okay, there is an answer to this question. This is called Dalton's law. It says that when you have gases which are close to ideal, then a total pressure of the mixture can be determined as a sum of partial pressures. And these partial pressures are related to, of course, they obey the same law of state here. So I can write that PO2 times V is nu O2 times RT. Now I write the same for nitrogen. And then I can sum up these two equations. And I get PV equals nu RT, where P is given by this. And nu is the total amount of matter, which is the sum of amount of oxygen and amount of nitrogen. So same equation of state. So this equation of state, thermic equation of state, can be applied to any ideal gas. And it doesn't even matter whether you have only a single type of molecules there or multiple types of them. When you have a single type of molecules, it actually means that they're exactly the same. As you know, for any atom, there are different isotopes. And any atom can have slightly different structure. So there are different isotopes. Even in a clean oxygen without any impurities, the oxygen molecules can be somewhat different. Too. So actually, yes, so this law applies to mixture of gases. That's good. Okay, now we are going to do a next step. The next step will be a process. So let's say I have some pressure, volume, but well, the description of the state of the gas is not the sole purpose of thermodynamics. Thermodynamics so engines the and so on and so forth. And the main purpose of this so to engine we need to introduce some dynamics into this. So before we have spoken only about the thermodynamic equilibrium state, which is reached after some time. But what we actually need is to describe process. Any process the change of conditions of the gas. That means that while we change these conditions during this process, we have and of course it becomes difficult to describe processes with additional approximations. One of them is the approximation called quasi-stationary process. It means that the process is so slow that each point of time at each time the state of the system is almost in thermodynamic equilibrium. Okay, so you change the external conditions so slowly so that after each change, it takes some time for the gas to adapt to to new conditions. But if you do this slowly, then at each point of time, your gas would be almost in this thermodynamic equilibrium. That's why by those small number of variables, and we can use all of these laws of thermodynamics to real process. But of course, slow in terms of your personal time. For example, this lecture is so slow, it takes so much time, 3 hours. Very difficult to have. Of thermodynamics, slow time can happen in the matter. So, of course, like you as an observer should not perceive the process as very slow. So it can be, but for the gas, this process, the condition that the characteristic time for the change of conditions should be minus relaxation time. As I said, in the minus first law, after some time you reach the state of thermodynamic equilibrium. That time, which is required for the gas to reach the state of thermodynamic equilibrium, is called relaxation time. So if you do your changes slower than relaxation happens in your system, then you have a quasi-station. The relaxation time becomes lower when the size of your system is lower. In this room, the relaxation is quite large. It can be very fast. Okay. So now let's try doing some processes with ideal gases. And okay. Some particular types of process you should pay attention to. One of them is the adiabatic process. Okay, try to remember your high school. What is the adiabatic process? It's like, you know, it's like a new language you should learn, like when you study this new terminology, adiabatic process, the process which happens without heat exchange. The amount of heat supplied to the system is 0. So you isolate your system from environment, and you can change volume, for example, but you cannot supply heat. So you can say that your system is inside some adiabatic case. No heat can be transferred from the outside to your gas, and it can be efficiently realized. As you know, like in every house, especially in cold environments, it's very important to have good thermal isolation. And that thermal isolation allows you to maintain the temperature comfortable for your living, and that temperature should be different from the temperature outside the house. And yes, so when you have this thermal isolation, then should spend lower. Okay, another type of process is process that you have constant volume. Or you can say delta V is 0. Okay. And especially when there is this ISO in the name of the process, that means something is constant there. Another process is either thermal process, or can be mistaken either thermal or either thermic. Don't remember now, actually. Probably either thermal. In here, which value is constant? Temperature. Another process is constant pressure. And sometimes a diabatic process is called isoentropic process. That means that you have constant entropy. Well, so far I have not introduced what entropy actually is, but that's for the following lectures. But these two terms can be used interchangeably. So I can say adiabatic, it can be also isentropic. Okay, and of course, when I write down all of these processes, I assume that my system is quasi-stationary, and that means that at any point of time, my gas can be described by a pair of variables, pressure and volume. Of course, if a non-equilibrium process happens, or a fast process which is not quasi-stationary, then this picture is no longer valid. So sometimes, the teachers like to ask during, like, write down, draw a process, and then, okay, the PV diagram process should be like initial state, final state, and the jump one to another. And while at any point on, because when you said non-equilibrium state is subjected to minus first law of thermodynamics. So when you describe equilibrium state, you need to describe pressures in all the space, temperatures everywhere. So no point on this, so only 2 points, initial and final point, when there is equilibrium. Okay, so these are most important. So let's write down the first law of thermodynamics to all these processes. Okay, I have started here. Let's continue here. Okay, adiabatic process, Q is 0. Then it's quite obvious. I can write that 0 is delta U plus W. Okay, but I have something missing there. I know only thermic equation of states. I know that PV equals nu RT, but I don't know what are U and W. Okay, for example, W can be determined because W is the mechanical work done by the gas. And mechanical work, by definition, is, remember mechanics, so that should be something like the integral of the force times the displacement, something like this. Okay, but this is not quite applicable to the gas, so we need to do some modifications. And for modifications, let's consider the following. So let's piston. A piston has the cross-sectional area of S. Here I have gas, which has some pressure, and I have a displacement of the piston. So now I can, in this simple system, I can determine the force which acts from the gas on the piston. The force of pressure is a product of the pressure of the gas times the area of the piston. Yes, and the displacement, so let's say delta x, some displacement. So I can determine the work as pressure times cross-sectional area times delta x. Okay, and now I look at this and see that this is actually the change of the volume. So the increase or the increment in volume for this gas. So I can write it as P delta V. And what's more important is that this particular case is a good case because in any general case, the work done by equal to P times V. Because you can consider, for example, you have some volume and everything changes, but you can consider this motion is like many pistons, very infinitely small pistons are inserted here and they change their positions. And after you integrate everything over this volume, you would obtain the very same result, that the work done by the gas is equal to P times delta V. Okay, the work was quite simple, but what about the internal energy? The question is whether, like, let's say we know this, we determine the internal energy. This. Of course, I think that most of you have seen the expression for the internal energy for the ideal gas before. But the question is, can it be derived from this? How do you think? Well, it doesn't, well, you see here pressure, volume, temperature, but nothing related to the internal energy. And, well, that means that probably pressure and volume, it's impossible to derive the internal energy from here. That's the second equation of state. This one is called thermic equation of state because this equation of state determines the temperature. But you need also a so-called caloric equation of state. Determines your internal energy. In the case of ideal gas, well, actually, what we can say about the internal energy of the ideal gas is only the pressure. Please note, this is a very good, this is a very important statement. It's a very strong statement because according to thermodynamics, energy should be a function of P and V, or for example, you can V and T. Since you have a relationship between pressure, volume, and temperature, you can derive or express any one of them as a function of the other two. So here the temperature is expressed as a pressure and volume, but you can find the pressure from here, like pressure is. And when you insert this into here, then you can obtain internal energy as a function of volume and temperature. And say that in the ideal gas, the internal energy is the function of temperature. That's a very strong statement. It says that internal energy at different volumes and this, which is actually, but of course, case, and this that internal energy is nu times CV times temp. What is this? Specific heat, it's a molar heat capacity. At constant volume. Molar heat capacity at constant volume. I will soon explain why it is so, but there is some constant here of gas capacity at constant volume. Actually, this constant is dependent. So in such a way that I don't add any information compared to this one. If I have some function of temperature here, so I had function of temperature here, and I go to another function of temperature here. And actually, but, well, this is wrong. What's actually correct? E of t to temperature, and here t prime. I here write t prime just to make the difference from this. This is one of for the energy. Prime. But of course, in school you had something more simple than this, like this. 3/2 nu RT. You probably remember something, yes? So that's internal energy for the single atomic gas. So if your gas is composed out of molecules which contain only one atom, then it's this. But if you have the gas which is composed out of molecules which contain two atoms, like oxygen or nitrogen, then you write 5/2 nu RT. That's the atomic gas. And here, 3 nu RT when the number of atoms in the molecule is larger than 2. Like, for example, if we have CO2 or something like this, 3 nu RT. But these expressions are actually in a limited interval of temperatures. And that would be discussed in one of the following lectures related to the theory of heat capacity, heat capacitance. So these are limited to a limited interval of temperatures, and luckily the conditions we are living in fall exactly in that interval of temperatures. So usually you can use these equations for the internal energy, for the ideal gas. times this equation is written like follows. I plus 2 over 2 times nu RT, or probably not I plus 2, just I. Just I, where I is a so-called, I is the number of degrees of freedom. Well, I don't think that this elucidates anything, but, well, this is a convention. The number of degrees of freedom. Okay, what is this? I will explain further. But this number of degrees of freedom is related to the number of atoms in one molecule. So when you have one atom, then the number of degrees of freedom is 3. When you have 2, it is 5. When you have 3 and more, it is 6. Well, to give you like a hint about what this degree of freedom actually is, it's actually the number of variables which are required to describe the motion of one molecule. So if single atomic gas, then you need only to provide 3 components of the velocity, Vx, Vy, and Vz, in order to find the energy of this molecule. So since we have 3 degrees of freedom, when you have a molecule which contains 2 atoms, in addition to these 3 components of velocity, you need to provide 2 angular velocities. So that's why you have 5 degrees of freedom. And also, when you have atoms, you also need to provide additional coordinate which describes the rotation about this axis. So that's why you have 6 degrees of freedom for 3 and more atomic gas. Okay. Let's make a 3-minute break and continue. Any questions about these caloric equations of state? No, yeah? Yeah, so in here, everything depends only on temperature. So when you have a fixed amount of gas, in here I have the simplest type of the relationship. It's proportional to temperature. But in the general case, for ideal gas, this is valid. Huh? Only for ideal gas. If you have the matter which is not ideal gas, then internal energy is also a function of volume. Sometimes it's even considered as a definition of the ideal gas. For example, the ideal gas is the gas in which the internal energy is independent of volume. But as I will show further, when you restrict your thermic equation of state to this, from this I can derive, really, I can derive that the internal energy is independent of volume. But I cannot derive how the function depends on temperature. That's why I have different equations of state for different types of molecules of gas, because, okay, you see they obey the same thermic equation of state, but they have different caloric equation of state. So that's why it actually proves that I cannot obtain this from that, because it depends on the internal structure. Okay. But in the general case, yes, you need to consider dependence on volume and temperature, not only on temperature. So just that there are many people here that the windows, as I see, they are closed, so that's for a time, the quality of air is constantly decreasing. And as the quality of air is decreasing, you are starting to get more sleepy. And also the quality of my lecture is also decreasing. So that's why it's very important to get a good air, at least. Okay, probably let's continue. Here we have the zero level problems. The problem number 2. I would like to draw your attention to this problem. The problem follows. We need to find the work done by a mole of air in the process at room temperature when the volume increases from V0 to V1, which is twice the V0. This important part was done by the gas is equal to P delta V, but this equation only applies when the pressure is constant. But what to do when the pressure is not constant? Then we need to do something similar to what was done when you consider the motion with the increase or decrease in velocity. So you need to replace this with an integral. And that applies to non-constant pressures. So in a sense, you divide your process into a very small processes. In each of them, the pressure is almost constant. And then you sum up all of these contributions. And from this, that integration comes. So in here, we know temperature is constant. That's why the PV is constant. So 1 mole of gas, that means that P is equal to RT. And as you increase the volume, pressure is dropping. And to include this, we need to replace this by integration. So the work done would be an integral of P dV from V0 to V1. And the pressure here becomes a function of volume. So that is RT over V dV from V0 to V1. And now so what would be this integral? So here RT dV over V. A logarithm, everyone agrees with the logarithm. Everyone understands why the natural logarithm appears here. So this, as you know, value of x plus, and you consider a definite integral, you take out this constant RT out of the integral and integrate within these limits, and that would give you RT times logarithm of V1 over V0. Another question is, okay, why V1 over V0? Yeah, the properties of logarithm. So the properties of logarithm, that logarithm A minus logarithm B is logarithm of A over B. Good. Good. So actually, since V1 is twice the V0, then I should replace this by 2. Oops, now it's a mess. RT logarithm 2. So I have chosen this example because it's a very important part, because I have shown you the formula P times delta V, but in here actually it's an integral. And in a general case, when you consider the work done by some gas, it's very good to draw the process in the PV diagram, because that integral of P dV is actually the area below the graph of the process. So that's this integral. So that's how the work can be determined graphically. Huh? Natural logarithm, yes. Natural logarithm 2 in there. Okay, and if you have a cycle, so the process which is repeating, then something like this in a single cycle. So from this point A to this point A again would be this, because this part which goes below is subtracted, because in here, in this part of the process, oops, in this part of the process, that's why here when I increase volume, I add the area, but when I go in the backward direction, I subtract the area below the plot, and what remains here is only the area encircled by my plot. Okay, so that's a work done in a cycle, in a cyclic process. Okay, and in here, the positive part goes above the part which has dV below 0. But of course, the process can be as follows. It can go in this direction. And when you have this type of process, the volume by gas is negative. So is this area multiplied by -1? Because in here you have negative contribution, and that negative contribution to the work is greater than the positive contribution. That's why the total work in this process is negative. In this is positive. You see? Like in here, the plot goes counterclockwise, while here it goes in a clockwise direction. So that's the difference. In a clockwise direction, the work is positive. In the counterclockwise, it's negative. In a process which is not cyclic, you just calculate the area below the graph. But of course, if it goes in this direction, then this area should be taken with the minus sign. Another problem, which doesn't require you to use thermodynamics, the problem 2.10 from Irodov. So it says that we have this type of a tube, and we have 2 pistons. We have air above. We have air below. And we have also some gas in between. And the pressure of this gas can be different from the air pressure. And also there is a thread which connects these 2 pistons to each other. And that mass of these pistons together is 5 grams probably. Yes? Oh no, it's 5 kilograms. Mass is 5 kilograms. Also, let me ask you, what is the air pressure under normal conditions? One atmosphere. 1 atmosphere is, well, about 100,000 of pascals. Yes. Well, of course, it's not exactly 100,000. Something like 101,000 and something like this. But for calculations, it's very safe to assume that the air pressure is 10 to the power of 5 pascals. But in here, we are not going to use this. It's just the related question. Okay, and also the difference in the cross sections of the top and bottom piston is delta S, which is S1 minus S2, is 10 squared centimeters. And the question is as follows, that, oops. The question is that we increase the temperature of the gas. And these pistons, they are displaced while I increase the temperature of the gas. And the question is, by which extent I should increase the temperature of the gas in order to achieve displacement of pistons by to shift the pistons through 5 centimeters. Okay, so, well, that's quite a complicated system. I would say that it has 2 pistons. There is also a thread and, well, quite complicated system. But the problem is it has a purely mechanical nature. So out of thermodynamics here, what I'm going to use is just the equation of state, that PV equals nu RT. So as I increase temperature, then either the pressure should increase or volume should increase, but nevertheless, PV should increase. And this is probably something which causes these pistons to move. But before, well, we should understand why these pistons actually move. And to do so, we need to consider the mechanical equilibrium of the system. One way to address the mechanical equilibrium of the system is to consider these 2 pistons. I label them 1 and 2, and write down their conditions for equilibrium. And, well, that can be done, but I'm going to do this in somewhat another way, because I don't like to have too many equations. And I'm going to consider the equilibrium of the combined system. This combined system would be composed out of pistons 1 and 2, thread, and also gas in between them. So according to the equilibrium conditions, the total mechanical force which acts on this combined system should be 0. So the force, the external force, should be produced by environment. And let's determine what environment here is. The environment is, of course, air above and below. That's environment. And also the environment is tube. So this tube is an environment which interacts with our system because it's in a close contact with it. And also Earth, which produces the gravitational force, which acts on both of these pistons. Okay, so let's consider the forces which act from all parts of this environment onto our system. From air above, I have the force which is P0 times S1. Yes, S1 is the cross-sectional area. Okay, F1 is P0 S1, where S1 is a cross-sectional area of the top piston. Okay, this force acts downwards. Another force acts upwards, and this is P0 times S2. So here, air below presses this piston, and this force acts in that direction. Also, I have, according to the third Newton's law, my gas in between these 2 pistons exerts pressure on side walls of the tube. But according to the third law, that means that side walls of the tube exert a force onto the air. And the direction of this force is opposite to the direction of this pressure. And as you see, when the side wall is vertical, then these forces are horizontal, and we don't need them because we need to consider the equilibrium in the vertical direction. So we can actually eliminate this. But what remains, what's the most important part which remains here, is the forces which are exerted onto these horizontal parts of the tube. So in here, my gas exerts pressure onto the horizontal part of the tube, and this force equals to P, where P is the pressure of the gas in between the pistons, times delta S, because delta S is exactly the cross-sectional area, or the area of the horizontal part of the tube. Because in here we have the area which is S1, in here we have smaller area S2, and this smaller area S2 plus this area should be equal to the S1. So this is exactly delta S. And the force exerted by gas acts downwards, but according to the third law, Newton's law, the force produced by the tube equals to P delta S, and it acts in the upward direction. Okay, the leftover force is the force of gravity, which is mass of the system times the gravitational acceleration. So the total mass of the system in here is presented by masses of the pistons, because I can neglect the very small mass of the gas in between the pistons and also a very small mass of the thread. So that's why the gravitational force should be mg. Nothing added. And then I consider a single equation which describes the equilibrium under these forces. Okay, so that would give me minus P0 S1 plus P0 S2 minus mg plus P delta S, and everything is 0 altogether. So, well, I can combine these two terms and get minus P0 delta S minus mg equals to P plus P delta S is 0. And from this I obtain that this pressure is actually equal to P0 plus mg over S. So this allows me to obtain the pressure of the gas in between these two pistons from a single equation. So once I do this combined system or compound system and consider the equilibrium of this compound system, I get everything in one equation. But of course, in the alternative way to do this problem solution is to consider the equilibrium conditions for each of these pistons separately. But in this way, you also need to introduce additional force which is produced by the thread. But in here, this force which is produced by the thread is the inner force of the system. It's not an external force, and this is immediately discarded when I do this solution. Okay, so when I increase the temperature of the gas, actually the pressure of the gas remains constant, because in here there is no variable which is related to the displacements of the pistons. So the pressure is constant, but since the pressure is constant, but the temperature is increasing, that means that volume should increase. And to achieve the increase of volume, I need to move my system upwards, because my volume is S1 times h, where h is the altitude. where h is the altitude of this first piston, plus S2 multiplied by L minus h, where L is the length of the thread. So the length of the thread is L, and it is constant. So as I increase h, then my total volume would be S2L plus delta S times h. So to achieve the increment of volume, I need to increase h. So that's what happens in this system. I increase the temperature, I increase this increment. So, okay, I can write like follows. Since PV equals to RT, then in the initial state, well, PV0 equals to RT0. In the final state, PV1 equals to RT1. Then I subtract the first equation from the second one and get P times V1 minus V0 equals to RT1 minus T0. Or actually, I can write that P delta V equals to R delta T. Delta V, from this equation, I can write that delta V is delta S times delta H. So now I get that P delta S times delta H is R delta T. From this equation, I obtain the final answer to this problem. Okay, there is no space here, so I'm going to go here and get delta T is P delta S delta H over R. And then I insert the pressure which I have obtained previously. Pressure is P0 plus mg over S, over delta S actually. So that would give me P0 delta S delta H over R plus mg delta H over R. The end. On the final step, I need to insert all of the variables which are provided in this problem to obtain the final quantity. I'm not going to do this due to the lack of time, so that's the end. So after that, everything is quite obvious. So there is no first law of thermodynamics in this problem, but nevertheless, this problem combines some mechanics with thermodynamics and achieves some very interesting condition. Okay, any questions about this? I recommend you to solve this problem at home if you have time. By writing the equilibrium conditions to the pistons separately and achieving the same result. So it would be a good exercise. Okay, the next part would be related to the lecture. So in this part of the lecture, I would like to discuss the polytropic processes. And heat capacity. Okay, so the heat capacity is a new concept that C equals to the amount of heat supplied to the system divided by the amount of temperature increase produced in that system. And well, for many processes, the heat capacity by itself is the temperature-dependent quantity. That's why oftentimes this quantity is understood in the differential form. So I consider a very small element of the process, and I determine a very small amount of heat which is transferred to the system in this process and divided by a very small increment of temperature. So this one is a more general definition, because this one implies that your heat capacity is constant, which is there is a proportionality between the amount of heat supplied to the system and the increase of temperature. But actually, it might not be so, and you need to consider a very small element of process in that way. Okay, so this is the heat capacity. Heat capacity is a function of process. So you don't only need to know which kind of a system you deal with, not only which type of gas you have or a liquid, but you also need to understand the process, because in different processes the heat capacity would be different. So this is not a property of the gas, it is something which depends on the process. Or I would not a property. Not a property, because it depends on the process. But once you specify the process, you can produce some properties, because once you restrict the process to isochoric process, V equals to constant, then this CV would be a property of the system. Of the system which you consider. And to obtain the physical property of the gas, I need to further divide this CV by the amount of gas by nu, and that would give me molar heat capacity at constant volume. And this would be the property of the material. So this is the property of the system. Once you divide by the amount of gas, you would get the property of the gas. So here is the system. Here goes the property of the gas. Okay. So that's definition. So if someone asks you to find some molar heat capacity or capacity somewhere, then you understand that this is a quantity which is related to the previously introduced concepts through this equation. Okay, now we are going to consider the isochoric process. Okay, so in isochoric process, the amount of heat in a small element of process equals to change of internal energy plus the work done by the gas. But since dV is zero, then there is no work being done in this process. No work being done. So the amount of heat equals to the increment of the internal energy. Okay, you should notice that I use somewhat different deltas when I consider the increment in this amount of heat, and when I consider the small changes of internal energy. And here I use the Latin letter D, and here I use small Greek letter delta. And there is a reason why I do this. The main reason is that U, internal energy, is the function of state. Is the function of state, while Q is not a function of state. It's a function of the gas and the process which happens. That's why delta Q would be different in different processes, while the du would remain the same in different processes. So in order to to make a distinction between functions of state and other quantities which are not functions of state, I use this small Greek letter delta for small increments of amount of heat. Okay, so now I have this du. So, okay, by definition, the heat capacity at constant volume is delta Q over dt. So this is du over dt. And to specify that I consider the process at constant volume, I add this additional subscript V. So in thermodynamics, when you see some derivative and there is something in here, that means that this derivative is taken under assumption that this quantity is constant. So volume is constant. Okay, and now we remember the equation for the internal energy, nu CVT. And if I differentiate this equation by temperature, I would obtain, okay, exactly nu CV, where CV here, as I said, molar heat capacity at constant volume. Okay, there should be some kind of a distinction, yes? So let's say I would denote molar quantity by also adding a small letter m here. Otherwise, there would be no difference between this CV and this CV, which label different concepts. So molar heat capacity. And as I said previously, CVM is 3 over 2R for single atomic gas, 5 over 2R for diatomic gas, and 3R for 3 and more atomic gas. Okay, so now you understand why this equation for caloric equation of state for the ideal gas contains this molar heat capacity at constant volume. Because this is because if you consider this process, what you obtain by dividing delta Q over dt is exactly the heat capacity at constant volume. Good. Now let's proceed and consider the isobaric process. P equals const. The equation of the first law of thermodynamics would be du plus delta V. Work is also something which depends on the details of the process. That's why I write delta here. So, okay. So now what I do? I again calculate delta Q over dt, and that would give me du over dt. Now, at a constant pressure, that's different from this one. This one was taken at a constant volume. Plus P dV over dt, again, at the constant pressure. Okay, now goes a bit of magic, and this magic says that actually du over dt at constant pressure is exactly equal for du over dt at a constant volume, because, because u is just a function of temperature for the ideal gas. And this is valid only for ideal gas. So for ideal gas, du over dt is always equal to nu CV. But in the more general case, if I have internal energy which is dependent on volume, then I need to go somewhat further. So if I have not an ideal gas, but something different, then I would say that du So let's say that U is a function of volume and temperature in general. So then it would be du over dV. So this is a partial derivative du over dV at the constant temperature times dV plus du over dt, partial derivative at the constant volume times dt. Okay, but do you understand what the partial derivative actually is? Yeah, okay, so you know, you don't know. No. Okay, it's very simple. If you have a function of multiple variables, for example, like this, x squared plus xy, you can calculate partial derivatives. A partial derivative is calculated assuming that this is the function of a single variable, while everything else, every other letter is a parameter, constant parameter. So if I calculate df over dx, then I have here a quadratic function. So that would give me 2x from here plus y from here, because y is a parameter here. But if I want to calculate a partial derivative with respect to y, then I assume that x is a constant parameter, but y is a variable. So in this way, I see a linear function with respect to y. So, and here is a constant. The derivative of constant is 0, plus the derivative of this is actually x. So that is how partial derivatives are calculated. So you assume that there is only the one variable, while everything else is just parameters here. And the same happens for this. So in thermodynamics, I also add what kind of variable I consider as a constant here. So du over dv at constant t, du over dt at constant v. Okay. So the general case is slightly more complicated. So while in the ideal case, the derivative at constant pressure and constant volume is the same, in general case, it's not the same. It's not the same. Okay, now finally I discussed this, where this comes from. Du equals to this times this plus this times this. So the reason why it happens is that, for example, you have two variables and you want to find the increment of your function when both of these variables change. So you can produce two small paths for this, and you can do the increment in two steps. First, you take one of these variables constant and increase the other one. So for example, here I have a function of temperature and volume. So here goes temperature, here goes volume. So first I fix the temperature and increase volume. Then the increment on this path would be equal to the derivative times the increment of volume. On the second step I go up. So I take my volume as a constant and increase temperature, and that would be produced. So it just goes in two steps. If you have a function of 3, 4, 5 variables, you need to add the respective number of terms here. So this is to be discussed in more detail in multivariable calculus in your mathematics courses. But yes, so the basics are like this. Okay, so now if I want to determine du over dt at the constant pressure, then I need to divide this by dp, everything. I need to divide this. Okay, I need to add here du over dv multiplied by increment of dv at the constant pressure plus du over dt at constant volume times increment of temperature at constant pressure. And this, if I have the equation of process, I'm sorry, it's somewhat messy here, but it will be more clear on the next line. the increment of volume at the constant pressure would be equal to dV over dt at constant pressure times dt. So now I get, in the final result, I get du over dV at the constant temperature times dV over dt at the constant pressure plus du over dt at the constant volume times dt. So you see the difference. Du over dt at constant pressure includes also the changes of volume which happen when you increase the temperature at the constant volume, at the constant pressure. So in here, when you have ideal gas, this du over dt is du over dV is 0. That's why I only left with this one. I'm only left with this one. So that's why du over dt at constant pressure equals to du over dt at constant volume. But in general case, it's wrong. This is the result. Okay, so this is du, yes, at constant pressure, and then I divided by dt to get this derivative. Okay, so this is a somewhat complicated part here. If you have any questions, please ask before you forget, or try to understand this as fast as possible after the lecture. Okay, yes?
Explain the first line, the du by dV with constant T and constant V, but constant pressure from where? Before, yes, it's before, a little bit back. Yes, this constant pressure.
Okay. I'm sorry. In here, I have written somewhat. Yes, I made a small mistake here. Let me correct this drawback. Thank you for this, for noticing this. I write here du at constant pressure. So du at constant pressure. So here is du for any process. Now I consider the isochoric process. So I get dV at constant pressure and dt at constant pressure. And then I derive this dV at constant pressure as this. And after that, I insert in here. So I get in the end that du at constant pressure is this. And after I divide it by dt, I obtain du over dt at constant pressure. And that would be, the result would be this expression in square brackets. So that's the final answer for the du. And of course, for the ideal gas, it's everything much simpler than that because, well, there is no dependence of internal energy on volume. Okay, so that's the isochoric process. But what I want to derive here is so-called Meyer's relation. So far I have discussed only the change of internal energy. Now we discuss the second part about PdV over dt at the constant pressure. So I write again that delta Q over dt is, okay, let's assume that I have only 1 mole of gas. I don't want to carry this nu with me everywhere, so I write here just Cv, the molar heat capacity at constant volume. And here goes plus PdV over dt. So here goes P and the partial derivative dV over dt at the constant pressure. I have 3 variables, pressure, volume, temperature. They are connected via the, they are connected via the thermic equation of state. So I can determine this one. Let me see, PV equals to RT for 1 mole. So now I can express the volume as a function of temperature and pressure. Volume is RT over P. So now I calculate partial derivative of volume with respect to temperature at the constant pressure. So what I see here, all constants except for this. So this gives me R over P. Now I insert this one into here. and get delta Q over dt at constant pressure, which is actually heat capacity at the constant pressure, equals to Cv plus P times R over P, and that would give me Cv plus R. So if you know the molar heat capacity at the constant volume, you can immediately obtain the molar heat capacity at the constant pressure by means of this equation. This equation has the name, okay, Meyer's relation. And of course, it is valid only for the ideal gas. And please note the very important part here. Well, actually, when I do these calculations, everything remains the same if I have the ideal gas which has the molar heat capacity at constant volume, which is the function of temperature. So of course, usually we assume 3 over 2R, 5 over 2R constants. But in the general case, the molar heat capacity, Cv, is the function of temperature. But Meyer's relation is valid even if this is the function of temperature, for any temperature. Okay, now we are going to finally discuss the polytropic processes. So that's about the heat capacity. Heat capacity is the function of process. And now I can search for processes which have constant heat capacity. So the polytropic process, is the process in which the heat capacity remains constant throughout the whole process. So not every process satisfies this equation because, okay, we can consider, as I have derived previously, the heat capacity at constant pressure and constant volume are different. So I can consider, for example, the following process as a single one, which contains a part which happens at the constant pressure and another part which happens at the constant volume. This process is not polytropic because the heat capacity here and heat capacity here are different. Here it's Cp, here it is Cv. So these quantities are different. This is not a polytropic process. However, these two parts of this process are polytropic. So the goal of my next derivation is to find out the whole family of polytropic processes. So I assume that the heat capacity is constant, and using this as a condition, I want to determine the equations of all processes which satisfy this condition. Okay, so this C is constant. Okay, so C is delta Q over dt. So this is okay, we also restrict ourselves to 1 mole of gas for simplicity. So that gives me du plus delta V over dt. So that gives me du over dt gives me Cv plus P dV over dt. Okay, so, well, as I see now, I have too many variables. I know that I have here pressure, volume, and temperature, and one variable is redundant. I can remove one variable. I can express, for example, pressure as a function of temperature and volume. So I insert this here. So that would give me Cv times plus RT over V times dV divided by dt. Good. So, and this is all equal to C. So from this equation, I can do the following. Okay, I get C minus CV dt over T equals to R dV over V. So this is after some algebraic transformations which I have done in mind, but believe me, this is how it happens. I get CV to the left-hand side, then I multiply it by dt, divide by t. What is left over here is R over V multiplied by dV. So this is the equivalent transformation. So now I have this type of an equation. This is called an equation with separated variables. This is a differential equation. So we are about probably half a year before you start differential equations, okay, we need to solve this somehow. And for solution, so this is called variable separation. Variable separation. And now we can integrate this equation. Now we can integrate this equation. So we write the following. C minus CV times dt over t integral equals to the integral of R dV over V. So that's the main procedure how you solve the equations with separable variables. And from this you get the following, that C minus CV times logarithm. Okay, let's do this from some initial conditions. This would be a logarithm of t over t0 would give me here R times logarithm V over V0. Okay. Now I need to calculate the exponential of this. T over T0 to the C minus CV equals to V over V0 to the R. And finally, after this messy set of transformation solutions and everything going on, I obtained the equation for polytropic process. It is T over, T to the C minus CV over V to the R is constant. Because this equals to the same expression, but with initial conditions, T0 and V0. So that gives you the equation for all polytropic processes. Okay, this can be also written in PV coordinates. To write this in PV coordinates, I remember that RT equals to PV. So actually, I can write the following. P to the C minus CV, V to the C minus CV over V to the R is constant. R to the C minus CV is also constant, but well, I haven't included into right-hand side. And after this, I get P to the C minus CV multiplied by V to the C minus CV minus R is constant, but I remember that according to the Myers relation, CV plus R would give me CP, so I get the following. Okay, P times to the C minus CV times V, C minus CP is constant. Often this equation is presented in the following way. It's presented as P to the power to V to the n equals constant where n is the polytropic exponent, which is given by C minus Cp over C minus Cv. Okay. So if I haven't messed anywhere, then that should be an equation for any polytropic process. And now let's consider some particular examples. So all of this derivation is to derive this one. Okay, let's start with the processes isochoric and isopotic. We know evidently that these processes are really polytropic. So this is P equals to const. How it relates to this equation? Well, if I take n equal to 0, that would be exactly it. So if I take n equal to 0, then v to the n would give me 1, and pressure would remain constant. And let's say, okay, let's assume that n is 0. So let's calculate this heat capacity. So that gives me C minus Cp over C minus Cv is 0. Okay? C equals to Cp. That's how it should be. Because when you have isobaric process, it's one of the particular examples of the polytropic process with n equal to 0. Okay, another example is V equals constant. That's the other case. We take n approaching the infinity. So when n goes to the infinity, so that means that this constant is mostly independent of this pressure. So when n is taken to the infinity, then essentially that means that we specify that volume is constant. And finally, I can get that C minus Cp over C minus Cv equals infinity. Okay, I can calculate the reciprocal of this value. So C minus Cv over C minus Cp is 0. 1 over infinity is 0. So that would give me that C equals Cv as it should be. Again, the isochoric process is one of the particular examples of the polytropic process, but there are two more examples. I'm sorry, probably you haven't written this one. So please interrupt me if I'm going too fast. So we're approaching the end of this lecture, and I'm trying to fulfill everything. And yeah. So can I go further? Yeah, okay. Okay. The other two examples are isothermic processes. Isothermic process, T equals to constant. Well, in this case, as you see, if I take dt equal to 0 and place it in here, that means that my heat capacity in the isothermic process is infinite. Because there is no temperature change, but there is obviously some exchange of heat. So if I take C equals to infinity, then my polytropic constant would be C minus Cp over C minus Cv. Okay, if C is infinite, then this is 1. So I get Pv equals constant. And now I'm also correct. Indeed, Pv equals constant is the equation for the isothermic process. So all of these processes are particular cases of the polytropic process. And another example, final example, is a diabatic process. In here, it's quite opposite. In adiabatic process, delta Q is 0. There is no heat exchange. But obviously, there are changes of the temperature. So my heat capacity in the adiabatic process obviously should be equal to 0. So if I take 0 to this exponent, then it would give me 0 minus Cp over 0 minus Cv. So that would give me Cp over Cv. And this is usually called gamma. And this is labeled as letter gamma and called adiabatic exponent. Wow. So In one action, we have determined the equations of all polytropic processes, and including the adiabatic.
Why go to one?
Because as I take this c to the infinity, then my c becomes much larger than all of these cp and cv. So my difference, infinity divided by infinity, but it's a particular case of infinity. So in order to overcome this, so infinity divided by infinity is called undefined, yes? But we can calculate the how it's called, derivative. So we can calculate derivatives over c, and the in the numerator we have 1 as a derivative, and in the denominator we have also 1 as a derivative over c. So this undefined expression gives me 1. Or I can actually explain it another way. Okay, c minus cp over c minus cv is like this. It's 1 plus, what's here? C minus cp minus c plus cv over c minus cv. So that c is eliminated. Here goes 1 minus r over c minus cv. And when I take this to the infinity, now it's no longer the undefined expression infinite over infinite. It's r over infinite value. So that goes to 0, and this is 1. So any explanation you like. So all of these are valid. So as I go to the infinity, that goes to 1. And probably, well, have you studied limits in calculus? So one of the approach to calculation limits is to determine which quantity is largest of them all. And then, okay, if you have, like, for example, some expression which is like x to the power of 4 plus something else, and here goes 3x to the power of 3 plus something else. When x goes to the infinity, then it's infinite, because the power here is greater than here. If they have equal power, then you need to divide the coefficients. If above I have less power than below, then it goes to 0. So yeah, this is one of the particular cases of such calculation. So as you see, all of these processes are particular cases of the polytropic process. Okay, and adiabatic exponent is the very important quantity. It's always larger than 1. And so next I would like to draw the process. So when I have isothermic process, I have this hyperbola. But when I have adiabatic process, since I have PV to the power of gamma, where gamma is greater than 1, then it goes like this. So the pressure in the adiabatic process decreases faster. And that means that actually that as I increase the volume in the adiabatic process, I produce some work. But in that process, I require to decrease the temperature, because I don't have any access to the external source of heat. So I can produce work only by decreasing the internal energy. So in the adiabatic process, the temperature is decreasing while I go to the higher volumes. Okay, how much time do we have? About 10 minutes, I guess, yes? Huh? 20 minutes, okay. So we are going to continue solving the problems. The next problem is 2.33 in the Irodov book. Let me see what's here. Okay. the problem 2.33 in Irodov book, it requires us exactly to calculate the adiabatic exponent for the gas, Cp over Cv, but we don't need to consider any processes at all. We just have a composition of gas. This is a mixture of oxygen, 2 moles of oxygen, and we have 3 moles of carbon dioxide. As you see, this gas has 2 atoms in 1 molecule, this one has 3 atoms in 1 molecule. So that's what's important in this mixture. And now we need to determine Cp over Cv. Okay, for the internal energy of the mixture of gases, we have the same equation which is similar to the Dalton's law. The internal energy of mixture is sum of the internal energies of all of the constituents of the mixture. We can use this to determine the molar heat capacity at the constant volume. So that would be nu O2 times the molar heat capacity for the oxygen is 5 over 2R. This is the gas with 2 atoms, plus nu CO2 times 3R, because the gas has, 1 molecule has 3 atoms. And now I can present it as follows. Times Cv, which I want to calculate. Okay, here goes temperature too. Okay, 2 times 5 over 2 gives me 5. 3 times 3 gives me 9. Altogether, it gives me, so this is altogether is 13. Okay, 5 plus 9, that's 14 RT. 14 RT, but sum of these two is 5 moles. So this would give me 5 times 14 over 5 RT. So that means that Cv is 14 over 5 R. Okay, in order to calculate the adiabatic exponent, we are left with molar heat capacity at the constant pressure. So I have Cv, I need Cp, and here I have mixture of ideal gases, which is ideal gas by itself. So I can apply Meyer's relation, Cp minus Cv equals R. So from this I get Cp equals to 14 over 5 plus 1 R. So this is 19 over 5 R. 19. And finally, I conclude the calculations by dividing Cp over Cv. This should be 19 over 5R over 14 over 5R. Finally, that's 19 over 14. 19 over 14. That's the answer to this problem. In terms of calculations, this problem is very simple, but the most important part of the solution is this one. That you calculate this internal energy of the mixture of two gases, and from that obtain the molar heat capacity of the mixture. And then you apply Meyer's relation and get Cp. The answer is here. Okay, so that was quite simple. Now we go to the next one, is 2.53a. Okay, we have 1 mole of ideal gas. Whose adiabatic exponent equals gamma. So that's a given. And we have a process P equals P0 plus alpha over V, where P0 and alpha are some positive constants. Find the heat capacity of the gas as a function of its volume. So this is not a polytropic process, unless we have some lucky coincidence. No, there is no lucky coincidence here. If P0 is not equal to 0, then this is not a polytropic process. That means that the heat capacity would depend on the point of this process you are actually located on. So let's draw a PV diagram for the process. So I have P0. So it actually looks like pretty much like an isothermic process, but the pressure is shifted by P0. So it's not an isothermic process. Okay, so now we need to determine heat capacity, and the only possible way to do this is to apply a definition. There is no other way to do this. We need to apply a definition. C equals to delta Q over dt in this process. And delta Q should be determined from the first law of thermodynamics. Delta Q is du plus delta V. So that would give me Cv dt plus P dV. So after I insert it here, I would get Cv plus pressure times dV over dt. The problem is that I don't know temperature. So I need to determine the derivative of volume over temperature, but I don't know temperature. Well, I know pressure and volume, so I can determine the temperature via the thermic equation of state. PV equals to RT. PV equals to RT. So I can write that P0 plus alpha over V times V equals temperature. So the RT, oops, not the temperature, but RT. From here I get that the temperature is P0V plus alpha. The temperature is P0V plus alpha. Okay, now we should somehow relate dV and dt, so I can just calculate the differential of this equation. I can apply the differential to the left side, to the right side, and I get that dt equals to P0 dV. Since everything else is constant, then no other terms are here. dt equals to P0 dV. So from this I get that dV over dt in this process is 1 over P0. Okay, now I'm concluding my calculation. So now I have this dV over dt. The pressure is already given, so I insert the pressure from here, dV over dt from here, and obtain my heat capacitance. Capacitor. Forgot the R. Where? Here. Yeah, sure. Thank you. R dt. R over P0. That should be correct? Yeah, that should be correct. R over P0. Yeah. Okay, so now I insert it there. So C equals to Cv plus P0 plus alpha over V times dV over dt. is R over P0. So that gives me CV plus, okay, I now have P0 plus alpha over V over P0 times R. And I can do the following, that this is CV plus, okay, P0 over P0 is 1, plus R plus alpha over P0V times R. This is CP. So here I get CP plus alpha over P0VR. Okay, that can be considered as a final answer, but now I look back and see that CP is not given actually. I only have gamma. I need to determine CP. I don't know CP. I need to calculate it. But I know that by definition, gamma is CP over CV. Yeah? And also, according to Meyer's relation, CP minus CV is R. So I can calculate CP in the following way. I can consider this as a set of equations. This is a set of equations. I have two unknown variables, CP and CV, and two parameters, gamma and R. So from here, I get CV equals to CP minus R. And after I substitute it here, I get gamma equals to CP over CP minus R. Okay, for solving these types of equation, I typically do the following step. I present it as gamma over 1, and then what I do? So I need to eliminate CP here, so I subtract numerator from denominator and get R. So I get gamma, numerator gamma minus 1 corresponds to CP. Here, CP minus R. So that is CP over R. So that gives me CP equals to gamma over gamma minus 1 times R. But if this method of solving this equation sounds quite unfamiliar to you, well, you can do this simply by multiplying both sides of the equation by CP minus R. You can get gamma over times CP minus R equals to CP. Then you open these brackets, expand here, and that gives you gamma minus 1 CP equals to gamma R, from which you obtain the same result. What I have used here is the stuff from proportions. So when you have A over B equals to C over D, I have used that A over A minus B is C over C minus D. So I can do it in any way you like. So this is a simple equation. That's actually a linear equation. Good, and now I have this CP, I can get the final answer here. This is gamma over gamma minus 1 times R plus alpha over P0 VR. That is the final answer. Okay, now we are left over with this text problem number 1. 5 minutes left, yes? Any question? Okay, so T1. This equation is related to the speed of sound in gas. So I'm going to introduce the equation during the solution, but I will derive it during the next lecture. So here, without the derivation. We need to estimate the relative accuracy delta C over C0 for the measurement of the speed of sound in carbon dioxide. And this measurement should be able to catch a small contamination of alpha, which is 10 to the power of 3 ppm of carbon monoxide. So here goes so we have a carbon dioxide with a small mixture of carbon monoxide. Are you familiar with these ppm units? No. This is extension of percent and promille. So percent is 1 over 100. 1 over 1000 is typically labeled as promille. So this is there is this sign. And ppm is actually 1 over 1 million. This is ppm. So that's so 1000 ppm is actually means that 1 promille of carbon monoxide. 1000 this is 10 to the minus 3 of carbon monoxide. Okay, so this tells us actually the number of molecules compared to the total number of molecules. So in the 1000 molecules of the mixture, there is 1 molecule of carbon monoxide. For the speed of sound, there is the following equation, gamma RT over mu, where gamma is the adiabatic exponent, which I have introduced before. RT, you know what this, and mu is the molar mass of this mixture. So the mass of the 1 mole of this mixed gas. So what we need to do is actually we need to calculate gamma and mu. Okay, gamma is Cp over Cv. And since this is ideal gas, I assume that this is Cv plus R over Cv. That gives me 1 plus R over Cv. So this reduces my problem from calculation of gamma to calculation of Cv of the mixture. And we have done this previously, 2 problems before. We have calculated the molar heat capacity of the mixture of gases. So that was, okay, so if I have part alpha of CO, that means that 1 minus alpha is CO2. This has the molar heat capacity at constant volume of pi over 2R. This has 3R. So that means that 1 mole of this mixture has the molar heat capacity of alpha times 5 over 2R plus 1 minus alpha times 3R. So that would give me 3R minus alpha R over 2. So there is a very small correction to the Cv. So that allows it to determine gamma. And finally, for the molar mass, I do the following. I multiply alpha times the molar mass of CO. This is 12 plus 16. 12 plus 16, that should be 28, plus 1 minus alpha times 12 plus 32. Okay, that should be 28 alpha plus 44 times 1 minus alpha. So that should be 44 minus 6, oh, not 6, actually 16 alpha. 44 minus 16 alpha. Okay, then I can insert this gamma and this mu into that equation and determine the correction to the speed of sound. Since we don't have any time anymore, then I would continue during the next class. So thank you for attention. If you have any questions, please don't hesitate and ask them. In the assignment, so here you have
can send this by email, right?
Yes, I'm going to share all the books and the syllabus with you. And also, okay, now I have 11 people attending, so I will bring 11 syllabuses for you to distribute, so for the convenience, so that you should have a printed out version of the syllabus.